adjust the chickpea can so that indeed you can hopefully see me and hear me fine. If not, let me know. Welcome everybody, welcome one and welcome all. Welcome to all of my continents tonight: Africa, Asia, Europe, North America, South America, Australia, Antarctica. Hopefully I'm not missing anybody. Welcome indeed, and hopefully everybody is taking care and staying safe in these times. Unfortunately, but relevant conversation or topic today is the atomic bomb. We will discuss the physics of the atomic bomb tonight with you guys. We have actually discussed it to some extent in the past when we talked about war, peace, and Einstein and his work, and how the E equals mc squared has a role to play in this devastating atomic bomb invention that happened around World War II. But even though it is widely known about and pretty much understood at this point, but actually less than 100 years ago, they were still kind of not sure how to do this, how to make use of the energy of a nucleus and turn it into a devastating and destructive bomb. This was not known. They kind of had the idea, but it was actually quite difficult. Especially, it was difficult to harness this type of energy in terms of the chain reaction that you kind of need in order for it to really become as destructive as people might have intended back then. And what is more, they actually did not have this figured out at all at once. It kind of took place in some stages, and we will read about that tonight, sort of as a history lesson, if you will, because there is much going on in this world, and it is good to be educated on sort of what all of this is about, especially in history, what it kind of looked like when people were working on this type of weapon, and what was sort of the premise of all of that, and how did all of the scientists kind of get involved, and what did they think, and what roles did they play, and so on and so forth, as well as all the various different countries at that time, Germany, the US, all of that. So we'll kind of address all of this as a history topic today. Hopefully you will get some value out of that. Let me go ahead and share the live first and do some buttons on my live settings to make sure everything's working correctly here on my laptop, and then we will get started. And yeah, the chat is open. Come on in. Welcome everybody. Welcome. Come on in, and you can put something in the chat and I will read it out. I spent at least a few minutes saying hi to everybody, and thank you. Hi Mike D. Mike D says hello, how are you? Everybody, thank you so much for being here, and welcome. Thank you for joining. Mike D is here. Who else? So if you're saying something in the chat, I will make sure to read it, unless it goes super fast. Sometimes that happens and then I cannot catch everything, but then at least at the end of towards the end of the live, I try to go back up and read everybody's comments, and especially kind of address any questions. So thank you once again for being here. How are you doing, Mike D? Let me share the live. So there are some crazy things happening in the world. Quite a bit of war and whatnot, and so I decided that we can talk about the physics of the atomic bomb, just so that we can get a little bit of a history lesson. Hi El Challen. El Challen says ciao ciao ciao. Mike D says, what did the frog say when his car broke down? Tell us, Mike D. Thank you for making any jokes. Total Vibes says hi. El Challen says WW3. Total Vibes says hi. Hi Total Vibes. I need to get it. Toad. Oh my gosh. Toad as in T-O-A-D. Love it. Thank you, Mike D. Thank you, El Challen. Welcome, Total Vibes. Thank you, everybody, for being here. Let me share the live, and we will get started on today's topic. And please, could you like the live, share the live, comment, give us some likes, and that would be really amazing if you could please support the Oh my gosh, PGR, so sorry about that. You missed my chat? Do you mean another live? Thank you for joining tonight, PGRE. Marshall Islands Joint Task Force 1. Wow. In the Pacific. So, okay. And sorry about being late tonight as well. Thank you for liking the live. Appreciate it. We want to get some engagement going here. Let people know we're live. I'll put that in my channel. So, you know, it gives me no joy to say that this kind of topic is relevant today. I'm not trying to scare anybody just because the US did recently carry out its strikes against the nuclear sites in Iran. I guess it becomes a relevant topic to understand why and what is sort of the significance of these types of weapons and what is sort of the history of this. Also, there might be some lessons in there, and also the history, of course. History is always important and interesting. So, we will get going. Let me make sure all of the live settings are good, and then we will get started. And we will keep it as a soothing, relaxing live. So don't worry that we're not going to cover a lot of the ongoing current conflicts. It's just going to be mostly a physics and history of physics as pertains to the war, or World War II, that is. So we're talking about the past at this point, okay? As sort of an educational topic. Yes, thank you, El Challen. So don't worry about it being disturbing. Not too disturbing anyways. Mostly just historical and so I also what I like about, well, I don't really like this topic, but it also lets us kind of review Einstein's contributions as well. Hi, Combat Sports, how are you doing? No politics, just physics. Yeah. I'm not going to discuss politics. Absolutely not. Just the physics. Physics of the atomic bomb. Physics. So, I think it's an interesting history. And also lets us review some things about particle physics. So we will go ahead and do that. Let me, let's see. Combat Sports, how are you doing? It's quiet. People must be really tired. I'm just making sure that the live is living. How is my... Can people hear me? Almost sleeping, I'll sleep by hearing you. Okay. Yeah, it'll be calming and soothing and peaceful. Even though it may not seem like that, I'll make sure to make it peaceful. We will have some peace in this life, if not in the world, but hopefully also in the world. What is the topic tonight? The topic is the atomic bomb. Sorry. The physics of the atomic bomb. So, you like it? Okay. God. Hi, Khalid. Okay, so as I was saying earlier, as much as it is sad, it is relevant today as we have all these conflicts in the world. And remember that such big conflicts were happening back when there was the World War I and then the World War II. So we have talked extensively about the physics of the 20th century, but something else that happened during the 20th century, along with all of the wonderful physics that took place and that we get to sort of review today, are the two wars. And actually the two wars in the 20th century did affect a lot of things and did affect some of the, not just some of the, a lot of the scientists of that time and their work. And, you know, at some point, some of them were busy kind of fleeing their countries and whatnot. So today we will reference this book called Einstein's Cosmos by Michio Kaku. We've actually spent some time on this book already in the past, but we will kind of review it again today for the benefit of people who might have kind of missed it in the past. And pretty much the point at which we will kind of pick up this topic from this book tonight is where Einstein has moved from Europe to the US already. So as you know, a lot of scientists were going hither and thither. Basically, they could not stay in their home countries anymore because of the world wars. And especially by the time World War II is happening, Einstein had already he had successfully fled and come to the US, and he was working in Princeton. So this is sort of the timing or the premise. And as you know, the E equals mc squared equation that is very famous and that he's known for, basically this conversion of a little bit of mass into a lot of energy is the main idea. But remember that that is actually not enough to make an atomic bomb. You need to kind of harness that energy and sort of start a chain reaction. And exactly how to do this chain reaction was something that really puzzled people, and they were not sure how to do it. Now, someone like Einstein, who had obviously worked on the very fundamental science without being motivated by any such practical application, if you will, as in those wars, he basically thought that this seems like something that, you know, basically some atom or a little bit of material and its glowing nucleus, if you will, with kind of giving off either radioactive energy or just that kind of energy, kind of told him that yes, the mass energy equivalence, the little bit of mass converting into a lot of energy, could be maybe used in a malicious way, as in the form of a weapon. But he didn't think that it would be so easy, and he didn't think that it could be possible. He didn't think it could be possible easily at all, and he thought that it's probably a practical application that will never happen in his lifetime. I don't think he paid too much sort of attention on it, or didn't think it was something that people would really care to do, or should do, because he kind of had some idea that it would be really devastating if people did do that. And really why he and others thought it was so difficult is not so much about the equals mc squared part. It's more really about harnessing it and what's the word, multiplying it, the multiplying of the effect of a lot of nuclei, the multiplication of this effect to then affect a lot of different multiple nuclei to then also release energy was really the challenge, and how to do that. Basically how to cut open, or how to cut through a nucleus of an atom or a heavier atom. This is basic science. Yes, this will be a science live, not politics, if that's what you're asking. So that was sort of the roadblock, is like they understood that you can kind of have an atomic bomb, as in get the energy out of an atom, get the energy out of a nucleus, but then how do you make it a much bigger effect by multiplying that, and how to cut open or slice many nuclei. So sort of the chain reaction part was a very difficult part, and they did not think that it would be possible. Einstein did not think it would be possible easily at all. So it's I think it's kind of interesting that actually it's really less than 100 years ago that in the year 1932, so this is what, 2025, so 100 years ago would have been 1925. So you know how the nucleus is protons and neutrons. Now depending on the exact element, however many protons are in the nucleus actually tells you the identification of that element, right? And then you also have this other thing, neutrons, we know now. But basically the neutron wasn't discovered until later, right? The neutron was discovered in 1932. So really, it wasn't until the discovery of the neutron that these types of things kind of fell into place, and we were able to slice open the nucleus and or cut a nucleus. And it's not until you can do that, like a chain reaction, to the point where then you can really think about nuclear fission as a mass destructive method. Okay, so that's sort of the history that we're going to cover today. We will read from the book, but basically people knew about atoms. In fact, people thought at one point in the journey of quantum mechanics and particle physics that the atom might be it, that is the most fundamental unit. But then they, as you know, the 20th century was very rich in making a lot of discoveries and doing a lot of work and progressing quantum mechanics a lot, and particle physics and the physics of the small a lot, to the point where not only the atom, then the nucleus was discovered, and people were like, okay, there's protons, and the number of protons gives you the type of element. But especially for the heavier elements, another thing that's very important in the nucleus is actually the neutron. And it turns out that the heavier you go, the very much heavier elements actually have much more neutrons. A little bit of Oppenheimer, yes. So the neutrons being a lot more is something that will also kind of play a role in this topic. And the neutron wasn't even discovered until 1932. So this issue of turning it into a chain reaction is where the neutron comes into play. Because basically the way nature had intended. So this story also kind of shows how I don't think that nature intended for something like the nucleus of a heavier atom to be sliced or cut, because just think about it. The nucleus has protons and neutrons. Neutrons are neutral, so protons are positively charged. So the nucleus is positively charged, and around the nucleus there's the electron, which is negatively charged, and so things are nice and good in the atom of an element. Hi, Crazy Sick One, how are you doing? And as you know, in electromagnetism, opposite charges attract and like charges repel. So we've talked also about the fundamental forces of nature. Over here, what's going to be important is the electromagnetic force between the nucleus of an atom and the electron. But if you're trying to say collide with the nucleus, and you're sending some kind of beam of something towards it, it's going to be difficult if depending on what you make that beam out of, because the nucleus kind of safeguards itself against things that are positively charged, because it itself is positively charged, and so you can't make it out of positively charged protons, for example, because it will get repelled. So turns out that neutron will be used to cut the nucleus, to do this slicing, which is basically needed in nuclear fission. And not only that, if you pick a heavier element, which once again, as I was saying, it will actually have a lot of neutrons. A heavier element like uranium has a lot of neutrons, right? It has some number of protons, and the number of protons gives you which element it is, but it has a lot of neutrons. And then if neutrons are used to cut this nucleus, that's actually going to help with the chain reaction. So it's kind of, I think it's kind of interesting how they didn't even know. I actually want to look up how many, I've forgotten. I know uranium is 92, but how many neutrons are, does anyone know how many neutrons are there in the uranium? Oh, I should have just done uranium-238. So I should have just subtracted it. So let's see. Let me be very, so look at this. Uranium-235, it's going to be 90. So we know that the atomic number of uranium is 92, which means that there are 92 protons. There's so many neutrons that I have to look this up. I actually don't remember, but I know that people say uranium-235, uranium-235, 238. Basically, that 238 or the 235 minus the 92 is however many neutrons there are. So this is what I was saying. And in fact, we have also mentioned how heavier elements, all of them, were made in stars, right? And so the process in which the elements are made is also different for the heavier elements that are heavier than barium versus, say, the lighter elements. Like, say, for example, lighter elements like the Big Bang gave us hydrogen and some helium. But then making hydrogen to helium and then lithium, beryllium, carbon, nitrogen, these lighter elements up to iron versus the elements that are heavier than barium, the processes are different. Even in the stars, how these elements are made are different. So at some point, it actually becomes very important to do this neutron capture in the nucleus of a heavier element, or basically in a heavier nucleus where there's a ton of protons, because basically these heavier nuclei are become very unstable, and you actually need more neutrons in order to kind of stabilize these heavier nuclei. So think about, I mean, hydrogen has 1 proton, helium has 2 protons. Depending on the isotope, it has however many neutrons, but it's only a couple, 1 or 2, right? Or 4 or whatever. And then the lighter elements it has lots of, it has the number of protons and then some number of neutrons, and it's not like a big difference. But for the heavier elements, you actually get a lot of neutrons per per nucleus. So keep that in mind as well. So the neutrons are very important, okay, in this whole topic. The neutrons are super important, and the fact that we didn't even discover the neutron until 1932, which is less than 100 years ago, and then that's what's important in terms of getting this cutting of the nucleus done. All of that together will give us the nuclear fission that we talk about today. So let's look at this book, what Michio Kaku has to say in terms of documenting all of this, and also he's talking from the perspective of these different scientists, that were operating at that time, and how their rules were kind of different as well. So for Einstein, he's already at Princeton at this point in the story. While at Princeton, he faced yet another challenge, the quest to build an atomic bomb. So we will see what that entails really. Turns out he wasn't actually directly involved in the Manhattan Project, because Einstein was very much under the scrutiny of the US government after he moved. They didn't really trust him to directly involve him in the atomic bomb work, okay? So back in 1905, Einstein had speculated that his theory might be able to explain how a small amount of radium could glow ferociously in the dark, its atoms releasing large quantities of power with an apparent limit. So I'm trying to find, I forget the exact, it's in the 1930s. We're in the 1930s at this point. So let's keep going. I think some of the years will get clarified as we keep going. So pretty much we're going a little bit farther back to tell you about how he was processing the energy of a nucleus if you were to mess with it, that type of thing. So let's read about that first. So back in 1905, back when he was giving us special theory of relativity, photoelectric effect, the old quantum mechanics, as in light has a dual nature, it is both a wave as well as a particle, that type of thing was happening back in 1905. Then the sort of teen 19s, like 1917, 1915, 1916, those were really important for general theory of relativity. By the time it's like the 1930s, he has had to move to the US, okay? So back in 1905, Einstein had speculated that his theory might be able to explain how a small amount of radium could glow ferociously in the dark, its atoms releasing large quantities of power without apparent limit. In fact, the amount of energy locked in the nucleus could easily be 100 million times greater than that stored in a chemical weapon. By 1920, Einstein had grasped the enormous practical implications of the energy locked in the nucleus of the atom when he wrote, "It might be possible, and it is not even improbable, that novel sources of energy of enormous effectiveness will be opened up, but this idea has no direct support from the facts known to us so far." So just about 100 years ago, we were very innocent as the human race. We had not figured out the atomic bomb yet, right? It is very difficult to make prophecies, but it is within the realm of the possible. In 1921, he even speculated that at some point far in the future, the current economy based on coal might eventually be replaced by nuclear energy. Because when they're seeing the stuff kind of glow and give off this energy, you can imagine that this sort of mass converting to energy thing was on their mind, and they were thinking, oh, this could be maybe used as for power. But he also clearly understood two enormous problems. First, this cosmic fire could be used to forge an atomic bomb with horrible consequences for humanity. He wrote prophetically, all bombardments since the invention of firearms put together would be harmless child's play compared to its destructive effects. So even though he thought it was far into the future that such a thing could even be done really practicably, he did have an appreciation for how big of a weapon, how destructive of a weapon it would become. He also wrote that an atomic bomb could be used to unleash nuclear terrorism and even a nuclear war. Assuming that it were possible to effect that immense energy release, we should merely find ourselves in an age compared to which our coal-black present would seem golden. Last and most important, he realized the enormous challenge in producing such a weapon. In fact, he doubted that it was doable in his lifetime. Turns out it was very much done in his lifetime, but he thought, again, for that reason that I was talking about, the whole point of the chain reaction and making something chain react like slice nuclei wasn't something difficult, or wasn't something easy, and he thought that that would be quite difficult to do. The practical problems of taking the terrible power locked in a single atom and magnifying it trillions of times was beyond anything possible in the 1920s. So again, 100 years ago, they did not know how to do this again and again and again and multiply that effect. He wrote that it was difficult as firing at birds in the dark in a neighborhood that has a few birds. That's what he wrote. Einstein realized that the key might be to somehow multiply the power of a single atom. If one could take the energy of an atom and then trigger the subsequent release of energy from nearby atoms, then one might be able to magnify this nuclear energy. He hinted that a chain reaction might happen if the rays released are in turn able to produce the same effects. So chain reaction means like the one thing gets the one nucleus cut, and then whatever happens with that will cut the next nucleus and the next nucleus and the next. So that's the chain. That's what we mean by a multiplied effect or a chain effect, where you do the one thing and then the thing you've done then does it again and again and again to many more nuclei to produce a much bigger energy. And this is what he thought would be very difficult. And it was difficult. It was difficult for everybody. If one could take so we just said that, he hinted that a chain reaction might happen if the rays released are in turn able to produce the same effects. But in the 1920s, he had no idea how such a chain reaction might be produced. Others, of course, also toyed with the idea of nuclear energy, not to benefit humanity, but for malevolent reasons. In April 1924, Paul Hartek and Wilhelm Groth informed the German Army Ordnance Department that the country that exploits it first will have an incalculable advantage over the others. The problem of releasing this energy is as follows. The nucleus of the atom is positively charged. So this is where we talk about the nucleus. This is where I'm interested. I like the basic sciences. So the nucleus of the atom is positively charged and hence repels other positive charges. Thus, the nucleus is protected against any random collisions that might unlock its nearly limitless energy. Because basically the other nuclei of that same material is also positively charged, right? So it's not like you can make two nuclei kind of collide or something and create some sort of slicing, because all of the nuclei are positively charged in that particular element, and in fact in any element they're always positively charged. Thank goodness we know that. Ernest Rutherford, whose pioneering work led to the discovery of the nucleus of the atom, dismissed the atomic bomb, stating that anyone who expects a source of power from the transformation of these atoms is talking moonshine. Some very innocent times back then. This stalemate was broken dramatically in 1932 when James Chadwick discovered a new particle, the neutron, a partner of the proton in the nucleus that is neutral in charge. So because it's neutral and it's not sort of important in identifying what element it is and all of that, it's got a very different kind of role. It has a very big role in nuclear physics, actually, in stabilizing these nuclei. Like I was saying, in the stars, the heavier elements are made via a different kind of process. They're made with nuclear fusion, which actually utilizes this neutron capture process. So it's very important, neutrons, turns out, in nuclear physics, but at this point, in the 20th century, when they're still discovering quantum mechanics and nuclear physics and particle physics, they had not discovered it. So they didn't realize that there was one more thing. So 1932 is the year. Unfortunately or fortunately, now they know about the neutron. If one could fire a beam of neutrons at the nucleus, then the neutron, undeterred by the electric field around the nucleus, might be able to shatter it, releasing nuclear energy. So, neutron being neutral could maybe be that beam that cuts a nucleus. So it's very interesting to me that something that they found extra in the nucleus was then used to cut the nucleus. You know what I mean? The thought occurred to physicists: a beam of these neutrons might effortlessly split the atom and trigger an atomic bomb. While Einstein had doubts about the possibility of an atomic bomb, key events leading to nuclear fission were accelerating. So now we have an year in 1938. So now we're in the 1938 year. Otto Hahn and Fritz Strassmann of the Kaiser Wilhelm Institute for Physics in Berlin electrified the world of physics by splitting the uranium nucleus. So not only did they find a heavier element type of atom to mess around with, they also now split it. And this is where things got very serious. They found traces of barium after bombarding uranium with neutrons, which indicated that the uranium nucleus split in half, creating barium in the process. So barium's atomic number is 56. And so you could imagine nuclear fission means to cut a nucleus. It means to... Hi, Sachi Mama. It means to break open a nucleus. So you might just make a lighter element in the process. So barium is a lighter element than uranium. Uranium is 92 atomic number. Barium is 56 atomic number. Someone should verify those numbers. But pretty much that's what they were finding, is that, oh my gosh, they were successful at cutting open the uranium nucleus. Very important person is in the next sentence here, Lise Meitner. I don't know if I'm saying her name right or not, but it's Lise Meitner, Meitner, a Jewish scientist and colleague of Hahn who had fled the Nazis. So this is another scientist who was very much affected by the war and had fled the Nazis. And her nephew Otto Frisch provided the missing theoretical basis to Hahn's result. Yes, this is Sachi Mama, one of my kitty cat babies. So Lise Meitner actually played a very important role. You'll find out soon here. So she had fled the Nazis, and her nephew also, but before fleeing, they got to kind of see what the Germans were up to. They were all working together. So their results show that the debris left over from the process weighed a bit less than the original uranium nucleus. So they were part of this work. Eventually, they fled. Yes, Germany. Yep, they were fleeing Germany. They were Jewish. So just like Einstein had to flee Germany, he was Jewish. He went to other parts of Europe first, but then eventually he came to the U.S. Same thing with Lise Meitner. She also fled Germany as a Jewish scientist, but she had some information, some very important information while she worked there that she realized, which is that they were messing around with the uranium atom. They were doing the research, how to split the atom, etc., or the nucleus rather. And they had, seen barium, so that means that they had actually successfully split the uranium nucleus. But also, this missing mass was very important. So where did this missing mass go, and where did this energy mysteriously come from? So upon weighing the debris, so it's sort of a before and after weighing of the materials, she found that the debris left over after this process was, it weighed a bit less than the original material. So it seemed as if the mass was disappearing in this reaction. So once again, results show that the debris left over from the process weighed a bit less than the original uranium nucleus. It seemed as if the mass was disappearing in this reaction. So you have to take very careful measurements to get this, but of course they were good scientists, so they measured it. The splitting of the uranium atom also released 200 million electron volts of energy, which apparently appeared out of nowhere. So this is actually going to be that E equals mc squared. But the person to, so even though E equals mc squared comes from Einstein, but the person to realize that actually this happens when you do this process is actually Meitner. So where did the missing mass go, and where did this energy mysteriously come from? Meitner realized that Einstein's equation E equals to mc squared held the key to this puzzle. If one took the missing mass and multiplied it by c squared, then one found 200 million electron volts, precisely according to Einstein's theory. So very great success of the mass energy equivalence of the special theory of relativity that Einstein gave us back in 1905, being confirmed now by Meitner in the year 1938. So literally in the context of the research during atomic bomb stuff in Germany, this person is realizing, oh my God, that missing mass and the missing energy, or the energy that came out, is literally equal, the energy E that came out is literally equal to mc squared, where m is that missing mass. So she had a very important role in sort of confirming this and understanding it before she fled Germany. Because Einstein, of course, worked on it. He gave us the theory, he contributed it back in 1905, but he wasn't the one who got the practical evidence of it, okay? Bohr, so Niels Bohr, another huge contributor to quantum mechanics at that time, when told of the startling verification of Einstein's equation, immediately grasped the significance of this result. He slapped his forehead and exclaimed, "Oh, what fools we've all been." In March of 1939, Einstein told the New York Times that the results so far do not justify the assumption of a practical utilization of the atomic energies released in this process. So because in 1938 the Germans made this sort of breakthrough in slicing the uranium nucleus, it was probably sort of I mean, I wasn't there at that time, but it was probably sort of in the news and people were talking about it. But Einstein was still sort of skeptical that there cannot be sort of a practical utilization because I think mainly he was doubtful of the ability to kind of multiply this effect. However, there is no single physicist with soul so poor who would allow this to affect his interest in this highly important subject. So I think also he was not a fan of the destructive effects of such a thing. So ironically, that very same month, Enrico Fermi, so this is March of 1939, when Einstein is basically writing off that this type of thing could be done and could be practical. But then in that same month, Enrico Fermi and Frédéric Joliot-Curie, so that is Marie Curie's son-in-law, discovered that two neutrons, so this is where it gets very serious. So these people, Fermi and Joliot-Curie, discovered that two neutrons can be released by the splitting of the uranium nucleus. So this is going to be where, so now not only have we discovered that the neutron exists, but now we have these two extra little innocent, not so innocent neutrons coming out of the splitting of the uranium nucleus, which will change everything. So this was a staggering result. If these two neutrons can go on to split two other uranium nuclei, then this would result in 4 neutrons, then 8, then 16, then 32 ad infinitum, until the unimaginable power of the nuclear force was released in a chain reaction. Within a fraction of a second, the splitting of a single uranium atom could trigger the splitting of trillions upon trillions of other uranium atoms, releasing unimaginable quantities of nuclear energies. Yeah, Fermi was pretty brilliant. So Fermi, looking out his window in Columbia University, mused grimly that a single atomic bomb could destroy all that he could see of New York City. So I can't believe you skipped over Strassman. We can talk about Strassman, but I'm following what's in the book. So this this thing about how to multiply the energy of that missing mass by basically these two neutrons. It seems like a small thing, but that small thing is actually going to affect and play the biggest role in the big thing that we talk about here, which is the atomic bomb. Because an atomic bomb is basically something that releases a lot of energy, and it has to be something that really kind of self supports, like one thing leads to another, which just kind of keeps on going from 1 to the 2 to the 4 to the 8. So this type of thing, like the number 2 is also really important here, that the fact that when you split that nucleus, you get 2 neutrons, which are 2 little extra things that can go and do that same thing of the slicing of the nucleus to 2 other nuclei, and then get 4, and then that 4 can go and split 8 other nuclei. You know, that is where you now have this multiplication effect, that chain reaction, and this is where now you're really going towards an unprecedented and a really dangerous amount of energy, which is exactly what they were intending with the atomic bomb, with this nuclear weapon. Okay, that's when you have a weapon and not just a tiny thing that's glowing without any chain reaction. Okay, so the race was on. Alarmed at the rapid speed of events, Szilard was worried that the Germans, who were leaders in atomic physics, there might be more about Strassmann here, I forget, because it's been a while since I read this in a lot of detail. So there might be something more here. So in 1939, Szilard and Eugene Wigner drove to Long Island to visit Einstein to sign a letter that would be given to President Roosevelt. Hi, Guru. Hi, PGRE. Hi, OTBHS. So this is a very important letter. So let's see what this is about. The fateful letter, one of the most important in world history, began some recent work by E. Fermi and L. Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Ominously, the letter noted that Hitler had invaded Czechoslovakia and had sealed off the Bohemian pitchblende mines, a rich source of uranium ore. And then the letter warned, a single bomb of this type carried by boat or exploded in a port might well destroy the whole port with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. As we know, they were not too heavy. They were transported by air at a later time. Alexander Sachs, a Roosevelt advisor, was given the letter to pass on to the president. When Sachs asked Roosevelt if he understood the extreme gravity of the letter, Roosevelt replied, "Alex, what you are after is to see that the Nazis don't blow us up." He turned to General E.M. Watson and said, "This requires action." Only $6,000 was approved for the whole year's research on uranium. However, interest in the atomic bomb was given a sudden boost when the secret Frisch Perls report reached Washington in the fall of 1941. So now we're in 1941. British scientists working independently confirmed all the details outlined by Einstein, and on December 6, 1941, the Manhattan Engineering Project was secretly set up. So Fermi and that other guy, Joliot Curie, basically had done the prototyping with the 2 neutrons coming out of splitting when you split the uranium nucleus. After that, you still have to perfect this whole thing and actually make it work and show that it works. And for that, they needed to set this up as a project and fund it and everything, and that's the Manhattan Engineering Project. And you will often hear that Fermi is very famous for obviously contributing to this. But you might wonder why, if E equals mc squared is such a big part of it, why wasn't Einstein part of the Manhattan Project? It's because they didn't trust him yet. Einstein had just not just come, he had pretty much had to flee from Germany to the US and he was still relatively new to the country, and he was in Princeton, he was working, and people didn't necessarily sort of trust him. The government did not fully directly trust him because he was kind of just got here from Germany more recently. So they didn't trust him. So he was not part of the Manhattan Project directly, but they did sort of consult him, and obviously his initial idea of the E equals mc squared is obviously a huge part of it. So under the direction of Robert Oppenheimer, so I know somebody requested Oppenheimer, who had worked on Einstein's theory of black holes. So sometimes black holes, sometimes bombs. Oppenheimer, very dynamic person. So he led this, he led the project, but under him there were hundreds of the world's top scientists were secretly contacted and then shipped out to Los Alamos in the desert of New Mexico. So if you, I've never been to Los Alamos yet, but that's where they all went. So actually, all these scientists kind of took a break from their usual basic science or fundamental science and physics and research projects, and they were all kind of now busy with this quite different thing in the Manhattan Project down in New Mexico. At every major university, scientists like Hans Bethe, Enrico Fermi, Edward Teller, Eugene Wigner quietly left after being tapped on the shoulder. Not everyone was pleased by the intense interest in the atomic bomb. So Lise Meitner, whose work helped to trigger the project. So Lise Meitner, remember, this is the person who had fled from Germany as a Jewish scientist, and she's the one who connected the dots between that missing matter and the energy that came out in the lab. So she was privy to that, so she was still part of the work there, and then she fled because, you know, being Jewish in Germany wasn't really working out much at that point. But she came with this very important information about the E equals mc squared connection and all that. So she could have also been a big part of the atomic bomb development, but actually she was not. A very strong character. So let's read. Lise Meitner, whose work helped to trigger the project, staunchly refused to be part of any work on the bomb. So she actually did not want to be part of the bomb. She wanted to stay true to her science roots and just do science and not deal with that. So she was the only prominent allied nuclear scientist to refuse the call to join the group at Los Alamos. So the only prominent allied nuclear scientist, just she really stood apart by refusing to be part of this endeavor. I will have nothing, so she said, I will have nothing to do with the bomb, she said flatly. Years later, when the Hollywood scriptwriters tried to glamorize her in the film The Beginning of the End as the woman who bravely smuggled out the blueprint for the bomb as she fled Nazi Germany, because that's what she did. She fled Nazi Germany as a Jewish scientist with this very important information. So they could have glamorized her and kind of made a movie out of all this and whatnot. They did make the movie, but she didn't want to be, she did not want to be glamorized in such a way. She really did not want to be associated with the bomb, okay? So she said, I would rather walk naked down Broadway than be part of this fanciful, scurrilous effort. Einstein was aware. So this was to do with all of these people, all these other scientists who were tapped on the shoulder. Most of them went to Los Alamos, and Lise Meitner did not. So she stood out, very much stood out. But the other person who actually kind of stood out is Einstein, because it was almost noticeable how they did not involve him in the Manhattan Project, because simply they did not trust him yet. But, you know, it was a little funny. Einstein was aware that all his close colleagues at Princeton were suddenly disappearing, leaving a mysterious mailing address in Santa Fe, New Mexico. Einstein himself, though, was never given the tap on the shoulder and sat out the entire war at Princeton. How nice. Or maybe not. I don't know. I don't think he would have liked to be part of the war, but he was not asked to be part of the war. So the reason for this, as in why he wasn't asked, has been revealed in declassified war documents Vannevar Bush, the chief of the Office of Scientific Research and Development and Roosevelt's trusted advisor, wrote, "I wish very much that I could place the whole thing before him." That is Einstein. But this is utterly impossible in view of the attitude of people here in Washington who have studied his whole history. FBI and Army intelligence concluded that Einstein could not be trusted. In view of his radical background, this office would not recommend the employment of Dr. Einstein on matters of a secret nature without a very careful investigation, as it seems unlikely that a man of his background could, in such a short time, become a loyal American citizen. So they did not trust him. In other words, simply put, the FBI and the government, and they did not want to include him in the Manhattan Project. Hi, Snow Kamoe. Apparently, the FBI did not realize that Einstein was already well aware of the project and, in fact, had helped to set it into motion in the first place. So it's one thing to be part of the basic science. So he was very much a part, if not the contributor, the main contributor to the basic science of this project, the E equals MC squared part of the project. But there's a bunch of classified details and things like that that the other scientists were read into, but he was not, because they did not trust him yet. McDonald's Trinity test site. I was doing another work. Okay. Einstein's FBI file was recently declassified, and it's very long. It's 1,427 pages. Edgar Hoover had targeted Einstein as being either a communist spy or a dupe at best. So they just thought that he was not the right person. They had some doubts about him. The agency carefully screened every piece of gossip about him and filed it away. Ironically, the FBI was curiously negligent in confronting Einstein himself, as if they feared him. Hello, XX. Instead, agents preferred to interview and harass those surrounding him. As a result, the FBI became a repository of hundreds of letters from every crank and paranoid. So, I think that is just the process of the FBI. I'm not, I don't think it's specific to Einstein. I think that's just what they do. If they want to get information about somebody, they're not going to go ask them. They're going to ask everybody around them and create a file and kind of make a decision based on all of that analysis if they trust the person or not. And in his case, they did not trust him. So, in particularly, they filed away reports that Einstein was working on some kind of death ray. In May 1943, a native lieutenant called on Einstein asking him if he would be willing to work on weapons and high explosives for the US Navy. He felt very bad about being neglected. That's just what they do, yeah. He had not been approached by anyone to do any war work, this person is saying about Einstein. Einstein, always quick with a quip, remarked that he was now in the Navy without having to get a haircut. The intense Allied effort to build an atomic bomb was stimulated by fears of the German bomb. In reality, the German war effort was badly understaffed and underfunded. Werner Heisenberg, Germany's greatest quantum physicist, was put in charge of a team of scientists to work on the German project. So there you go, Heisenberg right there. In the fall of 1942, when German scientists realized that it would take another 3 years of strenuous effort to produce an atomic bomb, Albert Speer, the Nazi armaments minister, decided to temporarily shelve the project. Speer made a strategic error, assuming that Germany would win the war in 3 years, making the bomb unnecessary. Nevertheless, he continued funding research on nuclear-powered submarines. Wow. Heisenberg was hampered by other problems. So even though they had made some good headway, there were some issues in Germany and some challenges that they faced themselves in the war. Hitler declared that ordnance development would proceed only on weapons that promised results in 6 months, an impossible deadline. So, you have to understand the atomic bomb was a pretty big research project that you can't just expect that they'll be done in a short amount of time. And there was tremendous pressure. So in addition to a lack of funding, German laboratories were under attack by Allied forces. in 1942. So doesn't help if you're constantly being interrupted either with attacks. In 1942, so for example, the strike that happened recently at those nuclear sites in that country, Iran. You know, imagine that sort of thing, right? It really interrupts your efforts, if you will. Now, if you are trying to interrupt the efforts, then that's a good thing. But if you are the one who is trying to do the efforts, then that's not a good thing. So in 1942, a commando squad successfully blew up Heisenberg's heavy water factory in Vemork, Norway. Poor Heisenberg, you know. In contrast to Fermi's decision to build a carbon-based reactor, the Germans chose to build a heavy water reactor that could use natural uranium, which was plentiful, rather than the extremely rare uranium-235. So yeah, Norway. In 1943, the Allies hit Berlin hard with saturation bombing, forcing Heisenberg to move his laboratory. So they wanted to use natural uranium, which was more than the than uranium-235. And the reactor that they were using, it was also different, which makes sense. Different people, different leads working on these different research projects in different places. So there might have been a lot that was similar, but quite a bit of the details were different as well. The Kaiser Germany versus US. The Kaiser Wilhelm Institute for Physics was evacuated to Hechingen in the hills south of Stuttgart. Stuttgart is in Germany. Heisenberg had to build Germany's reactor in a rock cellar in nearby Hagerloch. Under intense Loch, I believe, means lake, so it might be a lake. Under intense pressure and bombing, they never succeeded in sustaining a chain reaction. So I think the bombing and all the things constantly being destabilized does not help to sustain this technology. Meanwhile, physicists in the Manhattan Project were rushing to process enough plutonium and uranium for 4 atomic bombs. They were doing so. They needed the material to produce these 4 bombs, and being sort of a rare element, it's not like you can just go buy it in the shop, right? At one point, I don't know if you were here for the discussion that we had about Marie Curie, who discovered some heavier elements, including radium, radioactivity, polonium, things like that. Remember, we talked about how she was literally going, like, as an introverted person, she actually hated talking to people, especially about, like, not science, but she was going and, like, literally asking people to fund her project so that she can go buy some radium. You know, like, it's not like you can just buy this in the shop easily, these things, radium, plutonium, uranium. So having enough to make multiple bombs was not easy, okay? One second. So yeah, if you haven't seen our live that covers Marie Curie and her work, it's in the past. Several months ago, we talked about how she actually had to make use of some public relations expertise in order to kind of spread out, like spread the news about her work and get some funding to buy radium. So that kind of that just gives you an idea that these things were not easy to get. They were doing calculations right up to the time of the fateful detonation in Alamogordo, New Mexico. The first bomb based on plutonium-239 was detonated in July of 1945. After the decisive Allied victory over the Nazis, many physicists thought that the bomb would be unnecessary against the remaining enemy, Japan. So I believe this first bomb in 1945 was a test in Alamogordo, New Mexico, after the decisive Allied victory. So then, check the World War II facts, but they had pretty much obtained victory over the Nazis, and these physicists who were working on the bomb in Los Alamos might have basically hoped or expected that they're working on something that won't be needed. You know, sometimes you work on something as a strategic sort of advantage. Japan was going to surrender before they dropped the bomb. So sometimes you work on some new technology. So I'm trying to kind of give some idea about the physicists and the scientists and what they might have thought when they were working on the atomic bomb. Sometimes you work on defense projects and you work on technologies and things. You know that there is a chance that it might get used, but also you know that sometimes things have to be done as a research, as a strategy. It's sort of this strategic advantage that you have. Okay, and especially depending on the evolution of the war, it may very well not be used. So it's sort of, they were probably expecting that it won't be anything on their conscience, really. They might have worked on this technology. So we will talk about the differences between nuclear fission and nuclear fusion, if that's what you're asking. Is the hydrogen bomb nuclear fusion? I believe it is. So we can talk about that. Rishabh Sharma is asking, what's the difference between atomic and a hydrogen bomb? I believe the difference is nuclear fission versus nuclear fusion. What we're talking about right now is nuclear fission. The nuclear bomb, or the atomic bomb that we speak of at this time from World War II era, and which is now sort of relevant in terms of what's happening in the world, in terms of the sites that the US struck in Iran and such. And what is the importance of doing that is because atomic bombs are very destructive and very dangerous and very, very, very awful. Obviously, weapons of mass destruction is what they are. And we're talking about the physics of that. The physics of that involves nuclear fission. Nuclear fission is to cut the nucleus of a heavier element, such as uranium, plutonium, whatever else. And the problem is not just the point is not just to cut the nucleus, but also to multiply that. Like there's every time you cut the nucleus, some energy will come out, and that energy will actually be given by mass energy equivalence from special theory of relativity, which says E equals mc squared. So the little change in mass will actually give you a big release of energy, and that is the idea behind nuclear fission. So now what you want to do, if you want to actually utilize this and do this a lot, not you, generally, with something like a weapon, is that you would have to start off a chain reaction of this type of thing happening over and over and over and over. And it was actually quite difficult to cut the nucleus of something like uranium and then do it again. And once they figured that out, with a couple of neutrons being released from that process of cutting a uranium nucleus. That is when they made a lot of headway. So which reaction leads to more, oh my gosh, more destruction? By uranium atom or plutonium atom? I'm not sure. So, I guess plutonium is 94 atomic number. Oh, you know what? Here. Plutonium is heavier. So I guess whichever one is heavier, that might be the one, because that will involve even more neutrons and even more chain reaction capabilities. So the plutonium atomic number is 94. The uranium atomic number is 92. But then let me ask, how many neutrons in plutonium? Plutonium mass number, what is it? 244. So you've got plutonium mass number is 244 versus uranium is 235 or 238. So plutonium has more, yeah, it's gonna be plutonium, yeah, okay, yeah. Okay. Whatever mass change that you get by doing the splitting of the nucleus, whether that's a plutonium nucleus or a uranium nucleus, whatever little change in mass that will happen when the process is done, that is going to be equivalent to the energy that is released. So if there's more change in the mass, then there will be more energy released. But also, to sustain this type of thing in the form of a weapon, you'd have to, like I was saying, do this a lot. Do this again and again and again with a chain of events happening with the one nucleus to the next, to the next, to the next. So whatever happens with that first nucleus, say a couple of neutrons come out with in the case of that uranium nucleus, those two neutrons are going to slice the next uranium nucleus, and then the neutrons from that will slice the next uranium. Drop the bomb on me is a good song. And the next and the next. So the fact that it's a self-sustaining kind of thing, where the thing you're doing to slice the nucleus is gonna slice the next nucleus and the next and the next and the next. That's the danger of this whole thing. It's not so much that you cut one nucleus. I mean, that is pretty dramatic, but the fact that the doing of that cuts the next nucleus and the next and the next and the next, and every time you get E equals mc squared, every time you get that energy release is what makes this so destructive. Okay, that's where you get the big energy from, is the chain nature of this. Okay, so they thought, these scientists who were working on the atomic bomb back then, they thought that a demonstration atomic bomb would be enough, and nobody needs to drop anything anywhere. And pretty much they were thinking that we were looking pretty successful in the war, and so it would not be necessary to actually use these bombs on anybody. So some believed that a demonstration atomic bomb should be detonated on a deserted island, witnessed by a delegation of Japanese officials, to warn the Japanese that surrender was inevitable. So this would have been a lot more peaceful if basically this was used as a threat. Indeed, this is a big threat. So see, because now we know, the history is the history is not fun of this. Obviously, you know what I'm about to say. You know what unfolded back then. But so now we know how big of a threat this is. But back then, to kind of let people know how big this is, they thought maybe a demonstration would be enough. And honestly, that could have been a pretty good and peaceful option. Because if you just want to show that your weapon works really well, there could have been a more peaceful way to demonstrate that. Okay, so a lot of the scientists, remember, the scientists are not necessarily working on this, or they're not necessarily wanting that mass destruction to happen. They're working on it as a research project, and because it will make the defense stronger, and it is technology that they are coming up with. But yeah, anyway, others even drafted a letter to President Harry Truman asking him not to drop the bomb on Japan. So I think it was also a big weight on their conscience. I don't know. Somebody in the chat might know about the American politics at the time. I'm not sure why they dropped to. I don't know. Somebody who is American and American history specialist or knows the politics can chime in why they dropped any or two. But I wanted to tell you about the perspective of the scientists. I'm sure that many of them were wanting sort of a peaceful demonstration, or they were thinking it would be very unnecessary to drop any, or they were requesting the president to not drop any, okay? One scientist, Joseph Rodblatt, even resigned from the atomic bomb project, stating that his work was finished and that the bomb should never be used against Japan. He would later win the Nobel Prize for Peace. Nevertheless, the decision was made to drop not one, but two atomic bombs on Japan in August of 1945. Einstein was vacationing at Saranac Lake in New York at that time. Beautiful place, New York. That week, Helen Dukas heard the news on the radio. I believe this was, this might have been his assistant. That week, Helen Dukas heard the news on the radio, so he was on vacation. She recalled that the report said a new kind of bomb has been dropped on Japan, and then I knew what it was because I knew about the cellular thing in a vague way. As Professor Einstein came down to tea, I told him, and he said, "Oh, way. Oh my God," in his language. In 1946, Einstein made the cover of Time. Ominously, this time, hello Mike D. Ominously, this time there was a nuclear fireball erupting behind him. The world suddenly realized that the next war, World War III, might be fought with atomic bombs, but Einstein noted because nuclear weapons might send civilization back thousands of years, World War IV would be fought with rocks. So he became a big figure for peace, actually. So at first he was thinking that they will not get to the technology of sustaining the slicing of the nucleus and getting that energy out and doing that whole thing. There's Baji. So at first he was thinking that this is not going to be practicable. But then he saw that not only was it practical, they actually did it, and they even dropped a couple. So quite disastrous, quite literally disastrous. And then he actually became a very big proponent for peace in this world. So anyway, that year Einstein became chairman of the Emergency Committee of Atomic Scientists. So they didn't involve him in the Manhattan Project. They didn't involve him directly in the actual atomic bomb project. But once all of that, once the thing went down, he became chairman of the Emergency Committee of Atomic Scientists, perhaps the first major anti-nuclear organization. So these, this is the history, which is important to understand. Like, this is a very big deal. Hello, Tiger Face. This is a very big deal. After what happened, all of these efforts to get anti-nuclear programs up and running, to talk more about peace, and to understand like the repercussions of these things is really big, really great, and just don't go nuclear, right? Like it became sort of even a phrase, right? Like going nuclear on somebody means that it's the ultimate mass destruction. It's the ultimate destructive thing, and it should not be resorted to easily or at all, and one has to think through these things, and many more efforts need to be happening for peace and for there has to be sort of, if nuclear is a force, then there has to be an anti-nuclear force and efforts against it. Okay, so he became the chair for that and used it as a platform to argue against the continued building of nuclear weapons and to advocate one of his cherished causes, world government. Meanwhile, amidst the storm unleashed by the atomic and hydrogen bombs, Einstein maintained his peace and sanity by returning stubbornly to his physics. In the 1940s, pioneering work was still being done in the areas he helped to found, including cosmology and the unified field theory. This was to be his last and final attempt to read the mind of God. So that is the part from that book that I wanted to share with you again. So a lot happened in that time. A lot of scientists were very much derailed from their usual efforts and from their planned efforts to go kind of do things for the war and research technologies for the war. Einstein himself was sort of exempt from that. He was still in Princeton and he did not join the Manhattan Project. But of course, the world at that time, just think about it, like the atomic bomb, the hydrogen bomb, this was all that this was probably in the news and kind of what people talked about, the hot topic of that time. But he was determined to go back to his basic physics, the basic fundamental science that he cared so much about. And after this point, he continued until he died to work on the grand unification theory. So most of our live streams recently, we've been talking about the grand unification theory, which attempts to bring together general relativity and quantum mechanics and bridges sort of the gaps there, and is a broader theory, or attempts to be a broader theory that can subsume these other topics and explain things more generally. This is something that he really dreamed of, and he really wanted to achieve. And so even though everybody was talking about the wars and the atomic bomb, the hydrogen bomb, all of that, so nuclear fission, nuclear fusion, those technologies after being achieved became the hot topic, but he went back to his normal fundamental science and physics, which I love. He actually died without achieving success in the grand unification theory because it's very difficult, and at that time we still didn't know a lot of things. There were a lot of different discoveries and observations that have since then happened in particle physics, cosmology, etc., which gives us more information to work with when we attempt a grand unification theory now. But there's Baji. But that's what he worked on after all this stuff went down with the wars. So hopefully that gives you some idea about what the scientists of that time were kind of going through, including but not limited to Einstein. And really after all of this, the peace efforts became very much needed and something that he played a leading role in. I liked bin sub. Thank you for liking and subscribing. Thank you so much. Thank you for liking and subscribing, and thank you for joining. Can you do a super chat? Can someone do a super chat? That would be really great to get some support. But yeah, I wanted to share with you this history lesson of what happened about 100 years ago. Actually less than 100 years ago. 1940s is less than 100 years ago. And that even though, we talk about nuclear fission, nuclear fusion, people know that this involves the nuclei and E equals mc squared. I thought it was an interesting fact that equally, if not more important, was actually the discovery of the neutron by James Chadwick in 1932, which then led to the next events of then utilizing neutrons to cut open or to slice through the nucleus of uranium. And then not only that, that process creates 2 more neutrons, and then 2, so on and so forth. And that's how they achieved that chain type of thing, which is needed for the weapon. But so even though these types of things are so important in war and defense, this is hardly a fun topic, or something that is joyful. And indeed, we must remember that even back then, people were not really, it was unprecedented. The dropping of the 2 bombs in Japan was very, very unprecedented, and a lot of people who even worked on the bomb thought that it would just be a demo, and that's it, and it would be unnecessary to really deploy these against anyone. Okay, so hopefully that kind of helps with some of this history and also a little bit of the basic science of the bomb. Hopefully we will have more peace in the world very soon. Take care, everybody. Stay safe, and if you're traveling, safe travels. And let me know if you have any questions or any more thoughts. Let me know any more questions or thoughts. One of my cats is from Japan. His name is Gato. Gato. Raise a pigeon? Oh God. Well, don't fight, guys. PGRE said something about earthquakes, so that's very interesting. PGRE says that he or she does earthquake stuff. Nice chat. Thank you everybody for joining. Sorry it was a bit quiet today. I think people went to bed, or this topic is disturbing. Sorry if the topic is disturbing, but I think that it's good to know the science of such a thing, and also good to know a little bit of the history and put things in perspective. These things are never fun, and it's often too late before people realize that maybe a more peaceful approach would have been better. Okay, so I'm hoping that a peaceful approach is taken by all in the world, and that we all live happily and peacefully and healthfully. Okay, I'm going to read any last thoughts you have and say goodnight. I'll be back tomorrow, I think. What do you guys think? Tomorrow? So, the question about be back tomorrow. Thank you. The question about plutonium versus uranium, I actually looked it up. So I know that plutonium is heavier than uranium, but remember that it's that little change in mass which ultimately converts to the energy that's released from these bombs, right? So that change is not a whole lot different between the two. So just keep that in mind. So you can please do I'm looking it up actually because I wasn't sure myself. I'm guessing it has to do with partly that it's heavier and partly that because it has more neutrons, which is also the same thing as saying it's heavier. So so it's kind of like that mass change which happens when you fission a plutonium nucleus might be a little bit more than the mass change that happens when you fission a uranium nucleus. But really it's that mass change which will convert to energy release. So it's not necessarily a very big difference between the two, okay? You can look it up. I don't believe it's a very big difference between plutonium and uranium because ultimately it's that change in mass when you fission plutonium, and yes, plutonium has more neutrons. It's the change in mass, not the mass of the plutonium nucleus and the mass of the uranium nucleus. It's the change in mass in the plutonium nucleus upon slicing it, and the change in mass in the uranium nucleus upon slicing it. That change in mass goes into your E equals mc squared equation, okay? Delta mc squared. And that E is the energy that we're interested in, which is the energy release, which is in this case used destructively. So the change in mass may not be a whole lot different between the plutonium and uranium. I believe that the plutonium one is bigger, but it might not be so different from the uranium one, okay? Which is why I haven't heard significant, like obviously double check this, but I haven't heard significant sort of differences between, oh, was it plutonium or was it uranium? You know what I mean? Putting extra neutrons in my heart. Oh, thank you. Thank you for your support with these comments. Keeping it relevant, using neutron in your sentence is good. Off topic, you should read Plasma Physics for Astrophysics. PGRE is short for Post-Glacial Rebound Effect. Post-Glacial Rebound Effect. Oh, wow. Oh, because you work on geology? Is that why you have a glacial username? Post-Glacial Rebound Effect. Glacial Isotonic Adjustment. Oh my goodness, we have a geology person here. That's great. Yes, ma'am. Off topic. You should read Plasma Physics for Astrophysics. Okay. So anyways, this is obviously not a very happy topic, but I thought I'll cover it again because when we were covering Einstein, bingo. Oh, good. Well, that's great that we have a geologist with us. When we were covering Einstein's work, that was many moons ago. And I figured that a lot of the people are going to be new now and they might not have joined for that discussion. And it also goes to show quite the variety of contributions that we got from this guy, Einstein. And so much happened with every piece of, information that comes from him, really. Even the bomb, So hopefully that gives a little bit of a history lesson as well. gosh, I'm a little tired now. Tiger face is strange. Hi Dave, hello. Okay, Tiger face, are you gonna do a super chat? Or is it gonna be someone else? Dave, PGRE, OTBHS, everybody, thank you for being here. I wish that more people had joined today, because sometimes when it's quiet like this, it helps me. And other times when it's quiet like this, but a few people are commenting, it actually kind of is distracting. So I've got this happy medium now of like, when there is a lot of people, I have like, my brain does a thing where I can like focus on the topic and get that done and then interact with the chat again. But when it's a few people, I'm like looking at the chat, and that doesn't help. That does not help when I'm talking, but it's good otherwise. It's good when I'm chatting directly with everybody. Okay, let me share it and then I will take your leave. I can say good night to everybody. Good night, everybody. See you tomorrow. Bye bye. Good night. Bye, Dave. Good night. See you tomorrow.